there are two more rules of exponents we need to be able to understand and apply. Those are called the zero exponent rule and the negative exponent rule. Both of these are a little more abstract. We can't see these the same way as we can the product, quotient, and power rules just by multiplying out different terms. But both of these rules are necessary. They are a logical consequence of the earlier rules. They're necessary in order for the system of exponents to be consistent. So I just want to quickly show you a justification, a proof of each of these rules. Let's start with the zero exponent rule. X to the 0 equals 1 for any base not equal to 0. We would say that 0 to the power of 0 is actually undefined. But for anything else, x to the 0 equals 1. Why does this have to be true? Well, let's start with what we know. We already know that x to the m times x to the n equals x to the m plus n. That's the product rule we looked at, right? Well, let's ask this question. What if n equals 0? So let's plug in n equals 0 here. X to the m times x to the 0 equals x to the m plus 0. Or if I simplify this right side, I just get this. X to the m times x to the 0 equals x to the m. Now I could divide both of these by the amount x to the m. What do I have? Well, on the left side, I just have x to the 0. And on the right side, I just have 1. So we arrive at the conclusion x to the 0 equals 1. That's the zero exponent rule. So examples of this, if I have 2 to the 0, that equals 1, right? If I have 3xy to the 4th to the power of 0, all of that equals 1. That's the zero exponent rule. Now let's look at the negative exponent rule, which says that x to the power of negative n is the same as 1 over x to the n. And again, we'll go back to prove this to one of the rules that we already know. So we've already accepted that x to the m times x to the n equals x to the m plus n. And let's ask a question. What if n equals negative n? What if I would make that replacement over here? Let's see what we get. X to the negative n, x to the n equals x to the negative n plus n. Or, as I combine these together on the right side, I have x to the negative n times x to the n equals x to the 0. Well, we've already seen that x to the 0 equals 1. So this amount is equivalent to 1. Now, if I divide this by x to the n, on the left, I just have x to the negative n, and on the right, I have 1 over x to the n. Okay, so x to the negative 3 is the same as 1 over x cubed. X to the negative 5 is 1 over x to the 5th. Let's look at this one. 1 over x to the negative 2. If I replace this with its reciprocal, that's the same as 1 over 1 divided by x squared. I put 1 over x squared in the denominator here. That's the same as 1 times x squared over 1, which equals x squared. So 1 divided by x to the negative 2 is the same as x squared in the numerator. So let's apply the negative exponent rule to an exponential expression to see how this works. Here I have a to the negative 4, b cubed, over a to the 5th, b to the negative 2. I'm going to separate out the parts with negative exponents just to make very clear what is contained in this problem. So I have a to the negative 4 in the numerator. I'm going to take b cubed and a to the 5th, and I'm going to separate out the 1 over b to the negative 2. That's in the denominator. So this is just me expanding or separating the different parts of this problem. Well, we know a to the negative 4 is the same as 1 over a to the 4th. So this is 1 over a to the 4th times b cubed over a to the fifth times 1 over b to the negative 2. From the example that I did earlier with a negative sign in the denominator, we know that that's the same as b squared over 1. We're dividing by the reciprocal here. When I put all of this back together, I have b cubed times b squared over a to the fourth times a to the fifth. And then I combine like terms through the product rule using addition on exponents. B cubed times b squared is b to the fifth, and a to the fourth times a to the fifth is a to the ninth.